Hey everyone, let's talk about how the internet works. When your app calls an API, like api.github.com, a massive, almost invisible architecture springs into action before a single byte of data even hits your screen. Today, we're popping the hood on the internet's highway. And we're not doing this just because it's cool theory. Understanding exactly what happens between your device and a server, that's what separates average developers from the truly great ones. Every single millisecond of your API's response time depends entirely on this underlying journey.
Now, think about this tiny, almost imperceptible sliver of time, 100 milliseconds. To put that into perspective, it takes you about 300 milliseconds just to blink your eye. But in the world of API development, that fraction of a second is absolutely monumental. Take a real-world scenario from Amazon's engineering blog. They experienced a sudden, unexplained 100-millisecond bump in their API response time. And it wasn't just a quirky technical glitch. It had a massive, immediate, real-world consequence, literally causing a severe drop in sales during their high-traffic events. So what does that tiny bit of latency actually translate to in hard business terms? That 100-millisecond delay cost Amazon 1% of their total revenue. 1%. I mean, for a company of that massive scale, we are talking about hundreds of millions of dollars just evaporating. And why? Simply because a network request took slightly longer to resolve. Every millisecond of delay is quite literally a revenue leak. And that's exactly why we have to understand what's really happening down in the network stack. To make sense of this whole journey, we use a 4-layer model. It's kind of like a giant global postal system. At the very bottom, you've got the network layer. Think of this as the physical roads and highways connecting different cities. Right above that is the transport layer, which represents the delivery trucks physically driving on those roads. Next up is the security layer. That's your tamper-evident sealed envelope protecting whatever is inside. And finally, sitting at the top is the application layer. That's the actual letter, the HTTP data that you're trying to send and receive. Let's break down exactly how your API call travels through each of these layers, starting right at the foundation. Okay, so diving into the first layer. When your code calls api.github.com, the very first thing your machine does actually has absolutely nothing to do with GitHub. Instead, your computer basically has to yell out to the network, hey, what's the IP address for api.github.com? This happens because of DNS, the domain name system. Think of DNS as the internet's phone book. We humans are great at remembering names like GitHub, but computers and networks, they route data using raw numeric IP addresses. So DNS exists purely to translate those human-readable domains into machine-readable IPs, so your request actually knows where to go. The lookup process itself is honestly like this amazing high-speed relay race. First, your machine checks its own local cache to see if it already knows the address. If it doesn't, it asks a DNS resolver, usually provided by your ISP. That resolver then fires off a query to a root name server, basically asking, hey, who manages .com domains? The root server then points it to the top-level domain, or TLD server for .com. And finally, the TLD server directs the resolver to GitHub's authoritative DNS server, which proudly hands over the exact IP address, something like 140.82.121.6. And incredibly, this entire multi-step chain of queries typically finishes in under 100 milliseconds. Now here's the brilliant part. We don't actually have to pay that 100 millisecond penalty every single time we make an API call. Why? Because once that IP address is found, your machine caches the result for a specific window of time called the TTL, or time to live. Until that cache expires, your machine just completely skips the lookup process for any future request to that same domain. It's an incredibly efficient mechanism. But it's also the exact reason why, if you change a server's IP address, clients might still fail to connect right away. Their machines are stubbornly holding on to those old cache values until the TTL finally expires. Right, so now your machine actually knows GitHub's IP address, but it still needs to establish a connection. Enter the transport layer, and specifically TCP, or Transmission Control Protocol. TCP exists to guarantee reliable data delivery. Let's face it, the internet can be messy, right? Packets of data get dropped, they get delayed, or they just arrive completely out of order. TCP acts as this super responsible manager. It guarantees a reliable connection is formed, ensures all your data arrives perfectly in order, and automatically retransmits anything that gets lost along the way. But does it do all this instantly? Well, not exactly. Before a single piece of actual API information is exchanged, TCP absolutely insists on a formal introduction. We call this the three-way handshake. First, the client sends a SYN message, which basically says, "Hello, I'd like to connect." The server responds with a SYN-ACK message, saying, "Got it, I'm ready."
And finally, the client replies with an ACK confirming, "Perfect, the connection is open." Now, this rigorous handshake is great because it guarantees both sides are absolutely ready to talk. But it also adds an inevitable chunk of latency before a single byte of your actual data is even sent.
Because that three-way handshake adds all that extra latency, doing it for every single API request would be completely devastating for performance. And that is exactly where HTTP Keep Alive connection pooling comes in. Instead of opening a brand new TCP connection, doing the handshake, sending the data, and then closing it over and over again, engineers just reuse existing connections. By keeping the connection alive, subsequent API calls can completely bypass that handshake, avoiding the latency penalty and massively speeding up communication.
Okay, so we have our super reliable TCP connection, but there's a huge problem here. It is completely naked. Anyone monitoring the network can see exactly what's passing through it. That brings us to the security layer, TLS, or Transport Layer Security. TLS exists for one reason, to wrap that exposed TCP connection in an unbreakable layer of encryption. It prevents network monitors, whether that's some hacker sitting on public Wi-Fi or even your own ISP, from reading plain text data while it's in transit between the user and your server.
The difference here is literally night and day. Think about standard HTTP traffic for a second. Everything is completely visible. Your passwords, your API keys, sensitive user data, it's all just flying through the air in plain text. If you're on coffee shop Wi-Fi, anyone sniffing packets could just read your API keys right out of the ether. No way, right? But when you add TLS to create HTTPS, all of that data becomes encrypted random ciphertext. To an eavesdropper, it just looks like scrambled, meaningless noise. This is exactly why production APIs must absolutely mandate encrypted connections. It is non-negotiable.
So you might be wondering, how did two computers that have never even met agree on a secret code without someone else overhearing it? Well, the TLS handshake is basically pure cryptographic magic. It happens right after the TCP handshake. First, the client tells the server what encryption ciphers it supports. Then, the server replies with a verified digital certificate to prove its identity. The client double-checks this against a trusted certificate authority. Then, using some incredibly complex math, both sides derive a shared encryption key without ever actually sending that key over the network. And boom, from then on, they have a secure, private tunnel. Of course, all this back-and-forth negotiation takes time, and we already know how expensive latency is, right? Historically, TLS took 2 full round trips to negotiate. But with the introduction of the TLS 1.3 standard, engineers pulled off a brilliant optimization. They combined the steps and reduced the handshake from 2 round trips down to just 1. This effectively cut connection setup latency nearly in half, saving those precious milliseconds that, as we established earlier, translate directly to revenue. Now, even with pool connections and much faster handshakes, we still face a fundamental problem that code just cannot solve: geography. This is where CDNs, or content delivery networks, step into the picture. CDNs are these massive global networks that place servers at edge locations all around the world. The entire purpose of a CDN is to store cacheable API responses geographically closer to the end user. Because think about it, if your user is in one hemisphere and your server is in another, you're going to hit a wall.
And that wall is physics. Every single millisecond of network latency is fundamentally limited by the speed of light. Information physically cannot travel faster than this universal speed limit. If you have a user sitting in Sydney making an API query to a server in London, that request has to travel across the globe and back. The sheer physical distance guarantees they are going to experience unavoidable delays. We're talking around 250 milliseconds of round-trip time, just from physics alone, completely regardless of how fast your back-end code runs.
CDNs completely solve this distance problem by just not making the user go to London at all. When a user initiates an API request, the CDN intercepts it and routes it to the nearest local point of presence, or POP. If that local server has the cache data the user is asking for, it serves it instantly. The request never has to make those long transatlantic network hops. You were quite literally moving the server right into the user's backyard.
Let's look at a practical example. Think of a local weather API. Imagine thousands of users in London all opening their phones to check the local weather at the exact same time. Without a CDN, if the main server was in Sydney, every single one of those requests would take that 250 millisecond round trip. But with a CDN, the weather forecast is cached on a local London node. When the London user queries it, the local POP intercepts the request and responds locally, slashing the latency from 250 milliseconds all the way down to just 10. Talk about a game changer. Understanding the physical and protocol layers beneath an API call is the key to minimizing latency and securing data. Every millisecond saved across DNS, TCP, TLS, and CDNs translates directly to performance and revenue.